This is a video that goes with lesson 4 in unit 1, which talks about analog component identification. It's an introduction to resistors and capacitors. We'll use a lot of resistors in this course. We use capacitors a little bit for one particular activity where we need to use a capacitor. This lesson is just going to give you a basic overview of what they look like and how to read some of the coding on these components. So this presentation will introduce common components used in electronics, define a resistor and present various resistor types and package styles, demonstrate how to read a resistor's nominal value and how to measure its actual value with the DMM, define a capacitor and present various capacitor types and package styles, and demonstrate how to read a capacitor's nominal value. So that is what you should be able to do at the conclusion of this presentation. So a resistor, we have a nice picture of a resistor up here. Over here is the schematic symbol. It is the zigzag line. And this is what a resistor actually looks like when you are building a circuit. So we saw that a little bit in Tinkercad because they have the mock-up of it. And you'll notice these stripes that are on there. A resistor is an electronic component that resists the flow of electrical current. One of the questions in the last activity or 2 activities ago was what's the function of the resistor in the circuit? And the answer to that was it limits the current so that the LED doesn't explode on you. A resistor is typically used to control the amount of current that is flowing. Resistance is measured in units of ohms, which are represented by the omega, named after George. I think it's also Georg, because I think he was like German. Ohm's law defines the foundational relationship between voltage, current, and resistance. Here are your package types. So you've got carbon film resistors. Those are going to be the most common ones. And then 4 bands versus 5 bands. It has to do with the number of stripes that you see on them. Then we have variable resistors, also called potentiometers. Those are resistors where the value changes, and the little arrow represents that you can move along the resistor and you could create more resistance or less resistance. I'm sorry if I have a lisp. I have something in my mouth. I'm recording this, so and I'm kind of self-conscious about it. So anyway, this would be something like a dimmer on a light. For years, my parents' dining room light was a little knob you could turn and you could make it bright or dim. And then surface mount, that would involve the little prongs so that you can actually put it into a breadboard or printed circuit board. This is your size comparison, so you can see what the different size resistors can look like. And now we get into determining the resistor's value. So the resistor's value is going to be on the resistor itself, and that would be the color code. And then you have the actual measured value, which may or may not match up. It should be close. So resistors are labeled with color bands that specify the resistor's nominal value. That is the resistance that it is supposed to have when you measure it. And it's, what we would call the face value. And then when you actually put the multimeter on the resistor to measure it, that would be the actual resistance value, and they should be within a particular band around what the nominal value is. So here's your color code. Okay, so we have the first band, second band, then we have something called the multiplier, and then the tolerance. And so we get an idea of this going from left to right. All right, your tolerance is on the right-hand side, and then, so that tells you which way you need to hold it. Your first band would be either black to white there, so numbers 0 through 9. Then you have your second band. Your multiplier could be silver or gold also, and then that tells you what you're multiplying by. And then your tolerance is out here. If there is no band for the tolerance, so the tolerance can be either silver or gold, although we saw some last year that looked a little like they looked more orangey in color. They weren't, it was kind of weird. You could tell the difference between that and orange is just But if you don't see one, then the tolerance would be 20% on there. Now, you can look this up online if you need to. It is in your reference sheet for your EOC. So this is not something that you would expect to have memorized. If you were doing this all the time and you were reading the color codes all the time, you would memorize it by default. But this is not something that I am going to quiz you on. However, I will expect you to know how to use this once it is given to you. All right, so we have some examples here. So determine the nominal value for the resistor shown. So we look at the first digit here, okay, first band, and the first color band is brown, and so that corresponds to a 1. The second band is black, and so that corresponds to a 0. And then we need to go and look at our multiplier. The multiplier is this red color. And so when we look up red, it means we're multiplying it by 100. So we have 10 times 100, which is 1,000 ohms. Okay, and then you can leave it as 1,000 ohms, or you can use your SI and you can move your decimal point over 3 units, and that would give you 1 kilo ohm. So brown, black, red means that this is 1 kilo ohm. And that is a gold tolerance, so it's plus or minus 5%. We have a 5% tolerance on it. Example 2. So we have orange, white, and green. So orange corresponds to the 3. White will be down here. That'll still correspond to a 9. And then the green as the multiplier is covered up by my head, but you can probably figure out what it is because we're going from 100 to 1K to 10K to 100K. So sorry. I used to be able to make my face disappear, at least for me, so I could see underneath my little video face thing. And I can't. It's not an option anymore. So, yep, not an option. Okay. So that's times 100K. And then using your SI prefixes, you can move that around a little bit. That ends up being 3,900 kilo ohms. So pretty much what they're doing there is moving, multiplying by 100. So 39 times 100, and then that gives you the kilo ohms that way. So this is 3,900 kilo ohms, also known as 3.9 megs. So once you convert this to kilo ohms, you can move the decimal point over to get the 3.9, and that's going to go from moving at 3 decimal places up to moving at 6, which will change your SI prefix from K to M for mega. And that's okay. Engineers actually don't hold really fast to this, so you can actually see things given more than one way. So either one of those answers would be fine. There's not an obligation to write it a particular way. All right, so this is example 3. So this one, we are told what the actual resistance is, and now we've got to figure out what the colored bands are. So the first digit is a 1, which is going to correspond to brown. So the first one should be brown. Then we have the second digit is a 5. And so 5 corresponds to green. So the second band should be a green. Then we have to figure out that multiplier. So kilo is what? That we would multiply by 100 to get the kilo ohms. I have to think that one through. Hang on. So we have 1.5 kilo ohms. So that means we would take that decimal point and move it 3 spaces over. So 1, 2, 3 ohms. So that is 15 times 100, which gives us the red. So I don't think that one through. That's where I think I mentioned in an earlier video and in class that I'm not always really comfortable with the prefixes. Sometimes I'm more comfortable kicking back to the actual unit, but there's where the 100 comes from. So our next band would be red, and then it tells us it's plus or minus 5%, which would be gold. So what we're expecting is brown, green, red, gold. And so there we go. That's kind of fun little problem. That brings us to the measured value. So how do you use your multimeter to measure this? So when we go with the ohms, you do need to set it over here on ohms. So I think if I'm looking at that right, you got your ohms down here in the lower left. Now, what's not always obvious is which one of those settings should it be on. And if I did it all the time, I'd get more efficient at it. But you can kind of get an idea of what you think you're measuring, set it on what's close, and if the meter isn't giving you the reading you want, move it one to one side or the other side and see if you can get a better reading with that. All right, a capacitor is an electronic component that can be used to store electrical charge. It's kind of like a battery, except it drains really fast. And so and we will look at this a little bit, the charge on a capacitor, it'll like charge up and then it'll hold the charge as long as it's connected to power, and then it will discharge. And so you can end up with like waves that look like that, where you have like the charging and then it'll hold and then it'll discharge. Capacitors are often used in electronic circuits as temporary energy storage devices. So they will hold charge for a particular amount of time as they discharge. They kind of even look like a battery, except one, that's the schematic for it up top there, except one side of it is curved, the positive side is the straight side there. Capacitance is measured in units of farads, named after Michael Faraday, a British chemist and physicist who something significantly to the study of electromagnetism. I'm going to say contributed. Sounds like a good word. All right, so here are just some of your capacitors. We have ceramic discs, we have electrolytic capacitors, mylar tantalum monolithic ceramic. That is a mouthful. Here we have some more electrolytic. The ones that are most common, well, they look like this. They look like little discs or little cylinders. And you can see this is what's called a radial lead, meaning that both the positive and negative ends are coming out of the same end. Axial means that it's going through like an axis, so you have different types there. Surface mount capacitors, those would go on an actual surface, and we have the ceramic ones. You can tell they are much, much, much smaller than some of the other ones, so you see what they look like in comparison there. And then how to read the capacitor's value. So they're often printed on there, but there's a couple of things that you need to know, or at least know that you're assuming. So you have 10 micro on there, and so that can be read. It's pretty straightforward. That's 10 microfarads. And then it's plus or minus 20%. If you don't see a tolerance on there, then you assume the plus or minus 20%. Here you have 0.47 microfarads. This one has the units on it. This one doesn't, but it is assumed that you will know what the units are. So you can look right at the capacitors to see the capacitance. Disc capacitors have a code, and it just right through all those, didn't it? So we have 472K. All right. The first digit is the first figure, second digit, the second figure, third digit is the number of zeros. So it's like that multiplier. So we have 2 zeros, so 47, and then followed by 2 zeros. And then the fourth digit gives you your tolerance, which would be plus or minus 10%. So you have to know the code. Now, notes on disc capacitors are always expressed as picofarads. So if you're wondering, oh, wait a minute, how did you know it was a picofarad? How did you know that? If it's a disc capacitor, it's always expressed in picofarads. There's no absolute rule that determines which units to use for this, and I kind of mentioned that earlier. So you can say 4,700 picofarads, or you can say 0.0047 microfarads. Yeah. Now, this over here is the code. I'm not going to expect you to memorize it, but you should write it down. My face, the little video, is covering up some of it, so you probably should pull this so that you can see the entire chart, so you can pull the PowerPoint off of OneNote. All right, so here we have 331J. So we are to determine this. So 3 and 3 hopefully are pretty straightforward. First digit, second digit. Now that tells us the number is 0. So this is telling us there is 1 0. And then J we can look up right there. It is plus or minus 5%. So this is 330 picofarads plus or minus 5%. Here's example 2. That looks like 103. So the first digit is a 1, second digit is a 0, and then a 3 means it will be followed by 3 more zeros. And then K is plus or minus 10%. And so this would be 10,000 picofarads plus or minus 10%. And you could move your decimal point over. Okay, you can play around with that too. Might even be more, because 10,000 is kind of a big number. All right, so common other like electronic components. Number 1 is what's called a 7-segment display. This is what is on old school calculators and stuff, where you have your digits, digital clocks and stuff. So it's called a 7-segment display because there are 7 segments there. We can count them: 1, 2, 3, 4, 5, 6, 7. Sometimes a decimal point is also included. Here's what your LEDs look like, and again, as with Tinkercad, you have like a long end and a short one to differentiate between positive and negative anocathode. And then they put the dime here. That's not an electrical component. That's there for size comparison, so you can get an idea of how big they are. And what do we have here? Miscellaneous components. This is a fuse, this is a diode, and this is a voltage regulator. I can pretty safely say you will never need to know that for this class at all. So just enjoy that slide, study the pictures, and then move on and do something else. So this covers the material for lesson 4. And yeah, we'll just keep on keeping on. Let me know if you have any questions.